Today we're going to starting the electrostatic part of this lecture. So it is probably the beginning of the physics. Before we talk about it, we have to go through several the mathematic part, which was the last chapter. But now let's head on the physics. Okay, so electrostatic. So electrostatic is actually the most simple one and developed much earlier. Okay, so the outline of this lecture will be including the first one is the electric field, which is denoted as E, a bolt and uh, a vector. So electric field is a vector field or vector function through the entire space. And the second part will take the divergence of the electric field and the curl of the electric field and see what happened. And then because of property earlier, we talked about the mathematic, and we can define something new called the electric potential. We note it as V, which is a scalar field. Also is distributed all over the space, but it is a scalar. And it is much more useful later on because it is a scalar, it's easier to handle in compare with the electric field. The fourth part is the work and the energy in electrostatic. So we'll talk about the energy stored in the space and how much work we need to do when we encounter an electric field. And the last one is the conductor, and we'll talk about whatever we know most is the metals. So metal is a conductor, and we use metal to do wire to conduct electricity, so that's something we need to talk about. Okay, let's get started. So from the beginning is the electric field. Just like I said, electric field is a vector field, is a vector function through the entire space. And we'll use the Coulomb's law to describe the most fundamental property of the electric field. And of course, electric field itself. And continuous charge distribution. We know there's charge and there'll be electric field. So what's the relation? That's what we want to talk about. Okay, so starting with the source field and force. In electrodynamics, the electrodynamic means the uh, moving things, moving and time change, uh, the physics change with time, that kind of things. So electromagnetism will change with time, called electrodynamic, which is the title, the name of this book. Anyway, so the general goal is to figure out the force of attached charge experienced in a field contributed by source charges. Okay, so here are several things. Just like we said, there are force that is something we need to worry about, and also the the force is coming from the field, and the field is contributed by the source. So that's the idea. So and much later, the charge may be moving in space, but there will be the dynamic part. But now we only consider charge probably just distributed in space, like the plot here. So there are so many charges with the charge. We use Q as the symbol to describe the charge. And we use Q1, Q2, those lower script to describe uh, the the first one, the second one, and the ith one charge. And also, these are the charge that set the field in space. And then we have a charge that we want to try in space. When we put the charge capital Q here, we will figure out the force generated by this distribution of the charge and adding the field on that particular point, when we place the test charge here, it will experience some force. That's the idea. That's what we are trying to do. And in the electromagnetism, there's something really important. It's called the principle of superposition, which means the field generated by each charge is contribute at that particular point, And then the second charge, the first charge contributed here, second charge contributed here, and the nth charge contribute to exactly the same position. They can be directly summed together. So that is the principle of superposition that holds for linear system. But we are just stop here, and later on when we encounter some other linear system, we'll talk about it. But electric field is a linear system. So electric field is satisfying this superposition principle. Okay, so each source charge, these are the source charge Q1, Q2, and Qi, contributes to a corresponding field acting on the test charge with the force. So charge generates field at that particular point. So we place another test charge here. The test charge will experience a force. That's the idea. So different force contributed by different source charge can be vector sum. That is the superposition part that can be summed directly add up together. That's the idea of the superposition. Okay. With principle of superposition, if a method finding the force of each source charge adding on the test charge can be established, the total force on the test charge can be obtained by just add things up. And be careful here. So the force is also a vector. So these are vector sums. Okay? However, moving charge give a rather complicated form of the force. Speed of light will play an important factor. This part will be discussed much later, which is almost at the end of next semester on the electromagnetism too. Okay, now, therefore the story starts from stationary source charge. So here in this chapter, we only consider a stationary charge, means the charge doesn't move. That's it. That's the electrostatic, the static means. Okay, now, Coulomb's law. This Coulomb's law probably you have learned it much earlier. Okay, so under this stationary, both source and test charge are moving. So this condition, everything is standing still. The force between the source and test charge is satisfying this so-called Coulomb's law, which the force is a vector. And here are the constants here. And notice that there is a vector here, which is the funny R we talk about. And the direction is the source charge and test charge. From the source charge to the test charge, that is the direction of this funny R. And it is having a cap, so it's a univector. Okay, so we'll come back here later. Okay, so the coefficient part is this is a constant, and there's an epsilon now, which is called the vacant permittivity. So this value is 8.85 times 10 to the minus 12, and the unit will be Coulomb square divided by Newton dot meter square, or something like this one. Okay, and the charge are related because the source is contributed by the charge. So small q is actually what we here denoted as the source charge, and the unit will be in Coulomb. So either you write coulombs or coul, they'll work. And the test charge, capital Q is here, so the test charge, or this one. And the force strength, this coefficient is actually describing how strong the force or the magnitude of this force vector. And this funny R cap describe the direction. Okay, and interestingly enough, that the force is proportional to the inverse R squared. The funny R squared means the distance between the test charge and the source charge. Okay, earlier we defined these directional vectors, which from an origin or a reference point to the source, we use R plot, which indicate the source. And we use r without a prime, and both are vectors, denoted the vector pointing from the origin or the reference point to this observation point is this r. And this funny r also is a vector, is r minus r prime, both vectors. So this is the basic form of Coulomb's law, telling us the force the test charge experience is along the direction from your source charge to the test charge or the observation point. And it is proportional to the charge product of the source charge and the test charge. And also is inversely proportional to the distance between these two charges. Okay, that's the That's the idea. Okay, so it's very similar to the gravitation. The gravitation is something which is the gravitation constant here, and these are the masses, is exactly the same thing. Anyway, okay. So the electric field, E is actually the sum, just like we said, because the electric field satisfies the superposition principle. So the total force on the test charge, capital Q, is the vector sum of all force contributed by different source charge Qi. Like we mentioned earlier, we can have several charges, which is Q1, Q2 to Qi. So we just write everything down and sum them together. And we use this one indicate the first charge, and the first charge will have a funny R, and a subscript 1, which indicate the first charge to the test charge. And this is the distance. And the same thing for the second charge. Second charge second charge distance to the test charge, and the third one to the ice charge. So because of the constant and the test charge are identical, so we just write things down like this one. So in short, we can write as that the total force, the subscript TOT is the total force, is the total charge times the electric field, where the electric field at that particular point, we use R vector, which indicate the source. Sorry, indicate the origin pointing to the test charge, which is this R. Okay, so the electric field at this observation point can be written like this one, is the constant, and all the charges sum together. They'll contribute to the test charge or observation point, and sum because we have several of it. So from 1 to the nth charge. Anyway, that's it. So the electric field has a unit of volt per meter. That's the thing. This was to memorize it. And just recall the funny R is R minus R prime, which is the test charge and the source charge point, the vector. Okay, the vector from the origin to the point charge, test charge, origin to the source charge. Okay. When placing a charge Q in space, the charge constructs electric field everywhere in space. So we got source. The source generates field that is set up to the entire space, just like in the animate. So you generate the field or chi, so whatsoever. Historically, a virtual medium called ether is proposed to carry the field, but the concept was abandoned after the development of relativity given by Einstein. So don't know about it. It's just some historic stuff. Anyway, okay. So here is the example. 2.1 is finding the electric field at certain observation point P. So we got charge here, we got charge here. So basically, our charge set up the field at the entire space, but at particular point, the field is pointing from the source charge to the observation point. So it will be E1 contributed by the first charge, and this E2 is contributed by the second charge. So by that, we can use just simple idea. Our electric field is just the sum of the electric field of contributed by each source charge. So we write things down like this one. So by definition, we write down the first charge contributed to electric field 1 and second charge contributed by the electric field 2. So sum together, use trigonometry. This is almost trivial. So you try yourself. All right. So 2.1 example. And now the continuous charge distribution. Of course, here we might not encounter a just discrete charge like we described before, because we have some individual charge 1, 2, 3, 4 to I. But if we have a distribution of a charge which distributed in space, we can have it and written down in the integration form like this one. So constant remain unchanged, but the summation become a continuous distribution. So the idea is still the same. So distance from that particular source point to the observation point r. So we write things down like this one. And the only different things is changing the q into dq, which is the tiny bit of the charge, and taking the integration of the entire source space, that the part of the space containing source. So that's the idea. So if you have a particular space that has charge, that have tiny little bit of charge, and then the distance from this tiny bit to the observation point, you have funny r. So that will be summing all the dq through this source volume that will contribute to this observation point P. That is the electric field you write down. And this is a volume distribution, so we write things down like this. From time to time, we will encounter certain things like line charge, the charge distributing along a line. So we can do things like that too. So we will have a certain length contribute to the observation point. Of course, the distance still the funny r. Okay, and from time to time, sorry. So in that part, if the charge distribution along a line, we call it a line charge. So the same thing, if a charge were distributing on a surface, which is usually the case for the metal surface, you have a charge, so you have surface charge. So we write this one is lambda, is a line charge. We use sigma as the surface charge. So we have a surface, it contains charge and contribute to the observation point. Still, the distance is funny r. And so the volume charge, we use a volume charge, though, or volume charge density that inside this volume. So we'll have the same geometry. So here, okay, the lambda, sigma, and rho are presenting the charge density. So this is line charge density, this is surface charge density, this is volume charge density, and each have different uh, unit. The line charge is Coulomb per meter. This is Coulomb per meter square. So this is Coulomb per meter cube, like this one. So the dq, depending on what kind of geometry of the charge distribution, it could be the line charge density, Coulomb per meter, times the tiny little bit of the line integral element. That is the line charge density, Coulomb per meter. Or the surface charge density is Coulomb per meter square times the area element, and the volume charge density times the volume element. Okay, and here we use plus to indicate the source, because these are the charge which are the source of the field we want to discuss. So we use plus, just like before. we use plus to indicate source charge. Okay, so that's the idea. All right then. So by that, we can write things down like our electric field, just replacing this dq into, depending on the geometry, become lambda as a function of r prime, which is the distribution of your charge of the source space. And the funny r, of course, is from the source to the observation point r. So the L prime, that's it. That's the idea. Okay, so now the same thing for the surface charge and the volume charge. That's the idea. And the example 2.2. So if we have a continuous charge distribution and the same thing, similar to previous example, so we just write things down. But at this time, we have a continuous distribution, so we write things down like this one. And if the charge line charge density is lambda, so we just write every piece down. There'll be a dl, in this case dx. So we will contribute to the certain direction. And because we know it's symmetry, so we need to write things down or take the integration from minus L to L, and what's the direction, and how do they sum together. And here we know actually just along the z-axis because it is symmetry. So we can write things down. And please go through it. This is just some mathematic practice. All right.